Let's begin by discussing material properties. The materials panel in Fluent is shown on the right-hand side of the slide, and it can be opened by selecting Materials in the Project Setup tree or by going to Define Materials in the menu bar. There's an extensive standard database of materials in Fluent, and it's also possible to easily create custom databases of user-defined materials. The properties that you need to specify for a given problem will vary depending on which physical models you have enabled. If you're solving a multi-phase problem, then it's necessary to specify the material properties for more than one material. If you're solving combustion problems, then you have multiple gaseous species, and you need to specify the properties for each of the species. For problems with heat transfer, you need to provide thermal properties such as thermal conductivity, but if heat transfer is not activated, then the thermal conductivity entry will not appear in the materials panel. Similarly, for certain kinds of radiation models, the absorption coefficient is a required material property input, but if those models have not been activated, then the absorption coefficient doesn't show up in the panel. You can specify constant values for the properties, as we see in the graphic here, but you can also specify the properties as functions of temperature and/or mass fraction, or in the case of density, also as functions of pressure. These are just as built-in specifications, though. With user-defined functions, it is possible to define material properties as functions of other solution variables also, if that's appropriate. The Fluent Materials database, which is accessed by clicking here on the Materials panel, provides access to a number of predefined fluid, solid, and mixture materials. And if you look at the database panel on the right, you can see there's different material types that you can choose from, and also large amounts of available materials for a given material type. These materials can be copied to the case file, which you've already seen if you've completed workshop number 1, and once in the case file they can be edited if necessary. The user-defined material database feature allows you to create custom databases of material properties that you can load into Fluent and then access from the standard materials panel in Fluent. This means that if you have a particular case where you put a lot of effort into providing a precise, complicated property definition, then you can save that work in a user-defined database, and the next time that you need to use that fluid, you don't have to enter everything all over again. On this slide we have the most commonly used methods for specifying the fluid density. Other methods are available. These are just the most commonly used ones. For an incompressible flow where the density is constant or nearly constant, then you simply enter a constant value in the materials panel. For an incompressible flow where the density is a function of temperature, which is common in natural convection problems, then the density can be specified as a polynomial or piecewise polynomial function of temperature, or the incompressible ideal gas law can be used. In the incompressible ideal gas law, the local pressure is replaced by the operating pressure, and the operating pressure is representative of the mean pressure in the problem. We'll discuss more details of this in a minute when we get to slide 8. For compressible flows where the density is a function of both temperature and pressure, then we can use the ideal gas law. For relatively low Mach number flows, it's recommended to set the operating pressure close to the mean pressure of the problem to avoid round-off errors. And for flows with large, gradual changes in absolute pressure, like if you're filling a tank with a gas, then the floating operating pressure option can be used. Here we see a summary of all of the available options for defining the density, viscosity, thermal conductivity, and specific heat. All properties can be defined as being temperature dependent, and there's many options for the temperature dependency, including linear, piecewise linear, polynomial, and piecewise polynomial functions of temperature. All properties also have user-defined function options, and depending on which property, there's also problem-specific definitions. For instance, for the density, there's numerous real gas models that are available, or for the viscosity, there's numerous non-Newtonian models